So welcome back, everyone. Today we have Patrick Holzer from Fraunhofer ITWM with us. This is the fourth video lecture in series of the quantum machine learning lecture. So if you are joining in today or recording, maybe seeing the video recording on YouTube just today, I would recommend scrolling back on the playlist and going through the 3 lectures by Xanadu beforehand. Because today we'll be continuing with the 4th lecture. Today's lecture focuses on quantum neural networks, which in itself is a very important field, but also this is important for participants who are interested in doing the Fraunhofer Quantum AI project. So this particular lecture will directly be tying back to some of the fundamentals and some of the use cases, which are, which you do have to perform within the tasks for the project. So today we have Patrick with us. A little information about Patrick. Patrick completed his master's in mathematics from Technical University of Darmstadt in 2017. He worked as a software developer for a couple of years before joining as a research assistant at the Technical University of Darmstadt from 2018 to 2020. Since 2020, he has also been working as a research assistant at the Fraunhofer ITWM, and today he is with us. So the stage is all yours, Patrick. Over to you.
Thanks a lot. So as introduced, the topic of today's talk is focused on quantum neural networks and especially on the so-called frequency spectrum of it. I will explain what this is and Okay, so before I start, let me first summarize what I assume, what you should know. I assume that you have basic knowledge in quantum mechanics and basic knowledge in quantum computing. Nothing special, just that you know what quantum circuits are. Okay, before we talk about quantum neural networks, let's take the bigger picture and let's first talk about parameterized quantum circuits. What are parameterized quantum circuits? You know, you can build quantum circuits by smaller building blocks like the Hadamard gate, Pauli gates, and so on. And some of these small building blocks are dependent on some real variable, and that's typically an angle. Yeah, examples are, for example, the phase shift operator, or what we will use a lot in this talk is a unitary operator of the following form. You take e to the power of I times your variable x, and then some Hermitian matrix. This could be typically a multiple of the Pauli operators. Okay, so parameterized quantum circuits consists of these circuits, and some of them are dependent on some real variable, and the idea is now you can encode real hard data in your quantum circuit just by taking the real input as parameters, and there you can encode classical data. Parameterized quantum circuits are used in a lot of hybrid quantum algorithms, like for example VQA, GUAVA, QNNs, and some further ones, and why they are studied, why do people consider them? They're candidates for NISQ devices. Yeah, noisy intermediate scale quantum devices. Okay, so that were parameterized quantum circuits, and now let us define what quantum neural networks are. A univariate quantum neural network is a function of the following form. Univariate means here that you only have one real variable. Yeah, we will talk about it in a few slides, how to extend it to multiple variables, but for the second, let us assume we have a univariate model. And you see our quantum neural network is a function which is just the expectation value of some observable, where you start with your initial 0 vector and you apply some unitary, which is dependent on 2 types of variables. One is x, that is the data, and you have other parameters which are summarized here with theta, which encode, so to say, the weights. Yeah, like in classical neural networks, you have your input, your data input, which is called X, and you have your weights of your neural network that are the thetas here. Moreover, the unitary CU take a specific form for quantum neural networks. This is an image which I take from the paper from Maria Schult. The introduction follows a lot this paper that's very interesting to read, so I could recommend it. So how does the unitary look like? You have two types of unitaries you use. So you have one unitary which encodes your parameters theta, that's denoted by W, and you have your data encoding layers. If you don't like formulas, this image explains it a little bit better, I think. So this unitary consists of multiple layers, and each layer consists of a unitary which encodes your parameters theta, and you have your data encoding layers S. In that image, you see, okay, Maria Schult, in their paper, they assume that the data encoding blocks are all equal in each layer. You don't have to make that assumption, and we will talk about that later, what consequences it has if you assume that they're all equal or if you allow arbitrary data encoding layers. Okay, so just remember you have alternating unitaries, one encoding your parameters and one encoding your data. Typically, you don't allow arbitrary data encoding blocks. Typically, as mentioned on the first slide, you take data encoding layers of the following form. You take the operator e to the power of -I times your variable x times some Hamiltonian h. And through this talk, it's convenient to talk about generators. Yeah, so we call them generators. Okay, so that were the definition of univariate models. I promised I will tell you how to extend it to multiple variables, so multivariate models. I present two canonical ways to do that. One is the parallel ansatz. So what you do is you glue, so to say, models for univariate variables together along the qubit, so along the y-axis here. And mathematically, that's a tensor product. Yeah, I think that image explains it very well. So each of this block here only contains the variable x1 and so on, and this only contains the variable x index n. Okay, then if you have a parallel ansatz, you also have a sequential ansatz, and here you glue them together along the x-axis, so to say. So you glue different models consecutively at each other. So this first layers only contain the variable x1 and so on, and this layers only contain the variable x index n. Okay, so that were QNNs. Now the question is, how do I train it? And QNNs can be trained iteratively, very like classical neural networks. So what do you do? You evaluate your QNN function on a data set on quantum hardware. So here it is crucial that, that you evaluate it on a quantum computer or a simulator. If you want. One remark, you cannot directly measure this function or this value. So cannot measure the expectation value directly. So what you actually do is, for example, you measure you run it 10,000 times and then take the average, and by the law of large numbers, that should be very close to the expectation value. Okay, then you just do classical machine learning. You compute some loss on this output, and then you use a classical algorithm to update the parameters theta, so the weights. So to update these parameters, you typically want to apply some gradient descent or something familiar. So if you use real quantum hardware, you could use the parameter shift rule to compute gradients. On simulators, it's even better. So you have access to the Hilbert space, and then you can use backpropagation and backtracking and so on, because you have access to the Hilbert space. Yeah, okay. So with that, you can compute the gradients, and then you can do gradient descent like classical neural networks. And that is how you train quantum neural networks. Okay, so that was roughly the definition. So now let's take a closer look to the so-called frequency spectrum of quantum neural networks. So you may ask yourself the question, so what kind of functions, classical functions, mathematical functions, are represented by the class of QNNs? And Maria Schult et al. Gave an answer to that question, and they have shown that each quantum neural network can be represented by a finite Fourier series. Okay, so you see we have a finite sum, and the set capital omega is called the frequency spectrum of the QNN, and here you have some complex coefficients, and you have terms of the type e to the power of I times the vector omega dot product x. Okay, moreover, they have shown that the frequency spectrum, capital omega, only depends on the generators of your data encoding layers. And that is exactly what the image here should tell you. So the frequencies omega here, or the wavelength here, so to say, they only depend on the data encoding layers. While the coefficients, that are the amplitudes, depend on everything. So on the parameter encoding blocks, and also your observable n. Okay, and throughout this talk, just a small definition. If you read somewhere in capital R, that always means the number of qubits you could have, and L denotes always the number of layers we have. Okay. I want to give you a small impression on how easy this is to prove, and that you get an intuition of the mathematical analysis of the QNNs. I want to sketch the proof. I will do a lot of examples afterwards in this talk. So if you cannot follow each step, don't worry. Okay, so first, we start with, okay, we make the technical assumption, and I don't want to explain why, that the generators HL are already diagonal with respect to our standard basis. Okay, and now you remember in a quantum neural network, you have your unitary U, which is an alternating sequence between matrices W and data encoding matrices S. So to compute the action of U on the basis, you only have to compute the action of W and S on the basis. Okay, so let's start with W. And let's say, okay, we want to compute the action of W on some arbitrary Basel vector J. And we didn't make any assumption on the parameter encoding. So the only thing we can say is, okay, it's just a normal product between a matrix and a vector. Yeah, so you get this general expression. So you get the sum iterating over all basis vectors, and then you get the matrix entries here. Okay, more interesting is the action of your data encoding on the basis vectors. So you know, okay, by definition, we assume that our data encoding has this shape. And now we made the assumption that H is diagonal. And if it's diagonal, okay, then this is an eigenvector, and this is the eigenvalue, and lambda index j is then the eigenvalue of h index l corresponding to the base vector j. So you get an intuition where the Fourier terms comes from. Okay, and the next step is, okay, you want to compute the action of u on the state vector 0. You know that u is an alternating sequence of these operators, and you know, okay, from each w you get a sum. So that's why we have L plus 1 sums here, because we have L plus 1 w's, and we have L data encoding layers. And okay, you can group with the law of the exponential function these terms together in one exponential expression. And here the capital lambda is just the sum of the eigenvalues. Yeah. And this expression only comes from the data encoding layers, as we have seen. So it looks complicated, but it's not so complicated. It's just computing. Okay, and with that you can do further computation, but that's easy now. And what you get is you get a very large sum of this type. So you get here some coefficients, and these coefficients depend on all matrix entries in W's and the matrix entries in your observable M. And you get e to the power of I times x times differences of the capital lambdas. And now you can group these capital differences here together, and that is then your frequency spectrum. So that is a formula for the frequency spectrum, and we have seen why it's only dependent on the data encoding layers. Okay, so let us make a small example. So let's say you have a 2-layer and a single qubit QNN. Then you have 2 generators. Let's say, okay, the first one is the Pauli operator X. That's this matrix here, and this is eigenvalues 1 and minus 1. And let's say H2 is 3 times X. So let us then compute all possible values for capital lambda. And reminder from the previous slide, capital lambda are just all possible sums of eigenvalues of H1 and H2. So H1 has, for example, eigenvalue 1, and H2 has, for example, eigenvalue 3. So capital lambda could be 4. And you now can compute all 4 possible combinations. So minus 1 plus 3 is 2, 1 minus 3 is minus 2, and minus 1 minus 3 is minus 4. So the frequency spectrum now, according to the previous formula, is therefore given by all differences of these values. Okay, so let's compute all differences of these 4 numbers. So 4 minus 4 is 0, 4 minus 2 is 2, 4 minus minus 2 is 6, 4 minus minus 4 is 8, and so on. So you see, okay, the frequency spectrum of a QNN with these generators would have all even integers between minus 8 and 8. Okay, now you may ask the question, okay, that was interesting, but why is the frequency spectrum at all so interesting? Yeah, why you want to study it? Okay, so let us take a step back again and think about the goal in classical machine learning. In classical machine learning, you have given a target function, typically the distribution of your data. And then you specify your model. In classical machine learning, for example, a neural network. In quantum computing, that could be quantum neural network. And then you want to find parameters theta such that your model fits the target function very well. Okay, so now by the result of Schultz, we know, okay, quantum neural networks are finite Fourier series. And we know the more frequencies are available, the better the approximation of the Fourier series. I have to say, but for quantum neural networks, the problem is that these coefficients here depend on the parameter encodings, W and the observable M. The problem is you have only finitely many matrix entries there. So if you keep the size the same and you increase with some magical method the frequency spectrum, okay, you get more frequencies, but you get less freedom in the coefficients. So what could happen, and that's not clear if it happened, is that if you make the frequency spectrum larger, the approximation could get worse because you get less freedom in the coefficients. Or it could be the approximation quality could be not so good as you would expect it. But that's active research. Yeah, so at the moment, we just want to study the frequency spectrum and want to study, okay, how large can it be and how can we make it larger? And the idea is that then the approximation quality should increase. Okay, then the natural question is how to choose these generators such that the frequency spectrum contains many frequencies or maximally many frequencies. Can we say something about that? By the way, if you like analogons, you can think of these generators like the activation function of the classical neural network. Okay, so I didn't make any difference between univariate models and multivariate models. And I want to explain now why it's enough to study univariate models and we don't want to talk about multivariate models in this talk. That's a result you can easily prove. Okay, the frequency spectrum of a multivariate QNN, regardless of whether you use the parallel or sequential approach, is always given by the Cartesian product of the univariate models. Okay, so if you want to maximize the frequency spectrum of the multivariate model, you just have to maximize each univariate model or the frequency spectrum of each univariate model. So there's no complication by considering multivariate QNNs, and that's why we can assume at the moment we only consider univariate QNNs from now. Okay, so now we want to study the frequency spectrum a little bit in depth. For that, I do some notations and definitions. Again, it won't be too complicated, and I will make a lot of examples. Okay, first of all, you've seen that on a previous slide, the notation. That's just an abbreviation such that I don't have to write the set 0 to n-1 again and again. So for example, if you find a 5 in a square bracket, that means, okay, all integers from 0 to 4. And that's a crucial notation here. The set index n is just all integers from -n to n. Yeah, so if you find a set index 3, that's all integers from -3 to 3. Okay, that's also a typical notation. If you write a sigma and an operator here that denotes the set of eigenvalues h. So for example, the eigenvalues of the Pauli operator again are plus and -1. And maybe that now is a little bit new. So if you have arbitrary subsets of R to the n, then we can define the Minkowski sum of these sets. And the Minkowski sum are just all possible linear combinations of elements of these sets. So again, let's make an example. If you have the set 1 and -1 and the set 2 and -3, what does the Minkowski sum look like? It's 1 plus 2, it's 3. 1 plus -3 is -2, -1 plus 2 is 1, and -1 plus -3 is -4. Okay, so you see it's not very complicated. And last but not least, we define the different set of A that are just all possible differences of elements in the set A. Yeah, so for example, if your set A is the numbers 1, 3, and 5, 3 minus 1 is 2, 5 minus 1 is 4, 5 minus 3 is 2, 1 minus 1 is 0. And a crucial property by definition is that it's symmetric around 0. That means if a number, like for example 4, is in the difference set, then also the negative number, minus 4, is in the set. So it's enough to compute the positive differences, and the negative follows directly from this property. Okay. You don't have to remember the following properties. The only thing I want to say is, okay, all behaves very well, and you can compute like you think you can compute. Yeah, for example, the Minkowski sum and the difference set commutes. So it's up to you if you want to first compute the difference set and then the Minkowski sum, or first the Minkowski sum and then the difference set. The difference set is also compatible with the Cartesian product. The Minkowski sum is compatible with the Cartesian product. And last property is that the frequency spectrum of operators of this form here is equal to e to the power of, and this is now a set, and that's the Minkowski sum of the spectrum of the individual operators. And why is that important? Because we make a further assumption on our QNNs typically. So I said, okay, our data encoding layer is here. That's the blue box, has this shape. Yeah, e to the power of minus I times x times some generator h. And now what in practice, typically it's done, we say, okay, what are the generators h? Typically they are again made up by smaller building blocks, which we call subgenerators. So yeah, this image explains it very well. So in this image here, the subgenerators act on a single qubit, and mathematically it's the tensor product of the smaller building blocks. Okay. And that's why the property 4 is important. Okay, now back to the frequency spectrum. With that definition, we can reformulate the formula for the frequency spectrum. Yeah, you remember that was the formula on the previous slides, and we can reformulate it to that. Yeah, so the Minkowski sum over its difference set of the eigenvalues of the generators. Now, if the generators are made up of smaller subgenerators, like I said on the previous slide, then you can even split it further up, and then you get that the frequency spectrum is, now you introduce a second sum and you get nearly the same formula. Okay, so we have now a second formula. So let's maybe recompute the previous example again with this formula. So reminder, the previous example was we have a 2-layer model with a single qubit, and we say our generators are x and 3x. Okay, let us first compute the spectrum. For H1, it's the eigenvalues are 1 and minus 1. The eigenvalues of 3x is 3 and minus 3. Now let's compute all possible differences. 1 minus 1 is 0, 1 minus minus 1 is 2, and minus 2 follows directly. And okay, for H2, then you get the same computation, minus 6, 0, and 6. And by the formula here, then you know, okay, the frequency spectrum is the Minkowski sum. So minus 2 plus minus 6 is minus 8, minus 2 plus 0 is minus 2, minus 2 plus 6 is 4, and so on and so on. So you compute all possible combinations and you get the same set as previously. I mean, what do you expect? So you get all even integers between minus 8 and 8. Okay, so now let's compute a real-world example. So typically what you could do, for example, is you fix some two-dimensional Hermitian operator H, for example, some Pauli matrix. And let's say, okay, the eigenvalues are lambda and mu over it. And then the frequency spectrum of the univariate QNN with two-dimensional subgenerators, which are all the same, all are these fixed Hermitian operator H, is then given by this expression. So you have a scaling factor, which is the difference of the two eigenvalues, and then you have the set from minus r times L to r times L. Why is that? It's just an application of the previous formula. Yeah, so this is the general formula, and then okay, these H here, these subgenerators are all equal the one operator H, and the operator H has frequency spectrum lambda and mu. And what differences do you get? You get lambda minus lambda, lambda minus mu, and mu minus lambda, and this is exactly what stands here. Then you can shift the coefficient out, and then you have to make yourself clear that then the Minkowski sum of this set here is really set index r times L. For example, how do I get the number r times L? I add only once. Yeah, 1 plus 1 plus 1 plus 1 plus 1, and so on. And you have L times R summons, and then you get the number R times L. Okay, let us make a small observation. If we choose this ansatz for our for our QNN, you see, okay, the frequency spectrum is linear in R and L. So the question is, are there better choices for subgenerators? Maybe not constant, such that the frequency spectrum gets larger. The frequency spectrum is actually very small in this example, and that's because we have a high degeneracy here. What do I mean by that? Let's make an example. Let's say R times L is equals 4, and for convenience, we say, okay, the scaling factor is equals 1. We don't want to handle with the scaling factor here. And then the question is, okay, how do I get the number 4? Again, okay, it's just 1 plus 1 plus 1 plus 1. And that combination is unique. Yeah, with 4 summons out of this set, how do I get the number 4? That's the only possible combination. But that's not true for other numbers. Like, for example, I can write the 0 as 0 plus 0 plus 0 plus 0, or 1 plus minus 1 plus 1 plus minus 1, and so on. So you have a lot of combinations of how to write the 0. And that is called degeneracy. Yeah, you have multiple combinations to get the same number. And you remember that is the frequency spectrum. And if you want to make the frequency spectrum large, you want to have less duplicates. Okay, so now I show you some maximality results we prove. On the frequency spectrum, I want to show 3 of them for different settings. The first setting is this setting here. So we have a univariate model with equal data encoding layers. So the assumption Maria Schulp made in the paper. Yeah, so all data encoding layers are the same. And we also assume that our data encoding layers consist of 2-dimensional subgenerators, so that are these blocks only acting on a single qubit. Yeah, again, that are typical exponentials of Pauli operators. Okay, if we make this assumption, and now we call the eigenvalues lambda r and mu r, and now for convenience, let's make the assumption that the differences are ordered in increasing order. Then what we have proven is that the number k is maximal with respect to the following property. And this property just means that all numbers between minus k and k should be part of the frequency spectrum. Yeah, so again, we want to do Fourier analysis. So we want a large spectrum, and typically we want to have all numbers between minus k and k in it. Okay, so this k then is maximally large if and only if these differences are exactly this expression here. So that is just some integer. And moreover, you can give an upper bound on this k, and it's this inequality, and that's an equality if and only if the eigenvalues satisfy this property. Okay. Again, one observation. So you see this formula now is exponential in R. So remember in the previous example where we've chosen constant subgenerators, then it was linear in R and L. And here, okay, it's not exponential in L, but it's already exponential in R. Okay, if that was too complicated, again, let's make a numerical example. Let's say we're in the setting, we have a QNN with 3 layers and 2 qubits. Yeah, so this is our setting. And because we assumed all data encoding layers are the same, we only have to deal with two subgenerators, H1 and H2. And the requirements from the previous slides are now that, okay, the first difference should be 1, and the second difference is, okay, you plug in the numbers in the formula, should be a 7. Okay, so then now you have to find H1 and H2 such that the eigenvalues of it has difference 1 and has difference 7. What matrices do I know with this property? For example, we can choose H1 to be a Pauli matrix divided by 2. And there you see why you always want to have a factor of 1/2, because the Pauli X operator or any Pauli operator has eigenvalues 1 and -1. So the difference is 1 minus -1 is 2. So if you want to have a difference of 1, you have to scale it by 1/2. And if you want to have a difference of 7, then you scale it by 7. So you take 7 times Pauli operator half. Okay, now let's compute the frequency spectrum by hand. Again, okay, the different set of first eigenvalues are again -1, 0, and 1, and the different set of the eigenvalues of H2 are -7, 0, and 7. Nothing special. And now let's apply this formula we gave. And then you see, okay, it's the Minkowski sum of set index 3 plus 7 times set index 3. And now I claim that's equal set index 24. For example, how do we get the number 24? It's 3 plus 7 times 3. That's 24. How do I get the number 23? It's 2 plus 7 times 3, and so on. So make yourself clear that there are no gaps, that you really get set index 24. And now let's check if this really matches the previous formula for K. So L is now 3. 2 times 3 plus 1 is 7. R is 2. 7 squared is 49. Minus 1 is 48. Divided by 2 is 24. So now we build an example of a QNN under the assumption that all data encoding layers are the same. This has a maximum frequency spectrum. You cannot get larger. Okay, next question. Okay, let's drop the assumption that the data encoding layers have to be all the same. Now let's allow different data encoding layers. Again, the same notation. Again, we assume that we sorted the eigenvalues in increasing order. And then again, K is maximal with respect to this property if and only if the difference of the eigenvalues are powers of 3. Don't confuse yourself by this formula, the exponent. It just means, okay, you have the powers of 3. So 1, 3, 9, 27, and so on. And now, again, we can give an upper bound on K with equality if and only if this relation holds. And now we have 3 to the power of R times L, minus 1/2. And now you see this is exponential in R and L. Again, let us make an example. So because we now allow different data encoding layers, let's say we only have 2 layers and 2 qubits. So we have 4 subgenerators we have to specify. So the requirements from the theorem are now, okay, the first difference should be 1, the second difference should be 3, the third difference should be 9, and the last should be 27. And again, now I have to find some operators with these properties that the differences of its eigenvalues are these numbers. And now I choose, for convenience, x half, 3 times x half, 9 times x half, and 27 times x half. Again, you can compute the difference set, and that is just 3 times minus 101. Okay, and now let's again apply the formula, and now you get a Minkowski sum with 4 sets. So set 1 plus 3 times set 1 plus 9 times set 1 plus 27 times set 1. And again, I claim you can compute it by hand, but you can see it. That's equal to set 40. Yeah, it's easy to see why we get 40. 1 plus 3 plus 9 plus 27 is 40. How do I get 39? Okay, 0 plus 3 plus 9 plus 27. That was easy. But maybe we could have gaps. So make yourself clear why, for example, we get the number 20 by a linear combination here. And if you understand why we have powers of 3 here, you exactly understand the theorem. Okay, but maybe that's homework. For the last step, let's check that again the number here matches our formula from the theorem. So R is 2 and L is 2. So 3 to the power of 4 is 81. Minus 1 is 80. Divided by 2 is 40. So again, we have found an example of a QNN where the frequency spectrum is maximally large. You can't get larger. And you see, okay, even with 2 layers and 2 qubits, we already get 40 frequencies in our Fourier series. So that's really a lot. Last maximality result I want to give, okay, now you may ask, okay, that was interesting. So you made the assumption that your generators are made up of subgenerators, which always act on a single qubit. So they're 2-dimensional. And now the question is, what if you allow k-dimensional subgenerators? Okay, we also consider that. So these, in the paper of Maria Scholl, they called them G. So let's assume that G now acts not on a single qubit, but on, for example, 2 qubits. Then K is the dimension of the matrices, and Q is the number of qubits which they act on. That has to be the power of 2, because a single qubit has 2 dimensions, and you take the tensor product, then you get powers of 2. And we have to take the technical requirement that the number of qubits should divide capital R. That's easy to understand why, because, for example, if you have 5 qubits and you say, okay, my generator should use 3 qubits, then how can the second generator also use 3 qubits? That's not possible. Yeah, so if one subgenerator occupies q qubits, then the total number of qubits should be divisible by that. Okay, reminder that formula stays valid independent of what type of subgenerators you choose. We have to change some small thing, the index here, R divided by Q. Why that? Because, I mean, if you make the subgenerators larger, you have less of them. Yeah, so the sum here has to get smaller. Okay, and now we also change a little bit our maximality property. So in the previous 2 theorems, we asked ourselves, okay, if you want all numbers between minus k and k in the frequency spectrum, how can we make that k maximally large? But maybe that's not always what you want. Maybe sometimes you want to have that the frequency spectrum here, that's a set, contains maximally many elements. Yeah, so you now allow gaps and ask yourself, okay, gaps are okay for me, but how do I get maximally many elements in the set? And that is where degeneracy plays a role. So we want to have no degeneracy. And I give you an answer without a proof. That is what we proved, is that the frequency spectrum is maximally large if it matches this formula. Yeah, so this is the maximum size of the frequency spectrum you get. And you can see it's exponential in R and L, and it's even typically the numbers are greater than 3. Yeah, so the size is even larger. Okay, before I do an example again, how to construct such a QNN with maximally large frequency spectrum, let us think for a moment why this formula could be true, or when it's true. I said, okay, we want to have no degeneracy, so we want to have no duplicates. And where could duplicates come from? First of all, here you compute the difference set, and maybe, for example, you have the eigenvalues 1, 3, and 5, and then you have the difference 2 multiple times. Yeah, 3 minus 1 is 2, and 5 minus 3 is 2. So you don't want to have duplicates in the difference set. And this property is called Coulomb ruler. Just a quick definition. K many numbers are called a Coulomb ruler if and only if all pairs of differences here are pairwise different. And that means that the difference set of these numbers is maximally large. And if it's maximally large, how many combinations do you have? You have 2 times k over 2 plus 1 many combinations. Again, let's make an example. So, for example, if you have 3 numbers, 0, 1, 2, let's compute all differences. 0 minus 0 is 0, 1 minus 0 is 1, 2 minus 0 is 2, and that's the largest number you get, and that's all you get. And to get the negative numbers, okay, so we get set in x2, and that has size 5, and that's less than 7, which is what you get if you plug in 3 into this formula. So that's no Coulomb ruler. Let's check the numbers 0, 1, and 3. And okay, now you get all differences from minus 3 to 3. So they set index 3. And that has size 7. And that exactly matches if you plug in 3 into that formula. So that's Coulomb ruler. Okay, so we said the set of eigenvalues of these subgenerators should be a so-called Coulomb ruler of size k. And the second property we need to have that we have no degeneracy is that all linear combinations here I could build do not lead to the same number. So each linear combination should be different. And this can be achieved via scaling. So let's do a last example. So let's say now we have a single layer model. We have 6 qubits, and our subgenerators now occupy 2 qubits each. So they are 4-dimensional. Yeah, they are 4 times 4 matrices. Okay, first of all, we have to find then a Coulomb ruler of size 4, and I claim that 0, 1, 4, and 6 are Coulomb ruler. Let's check that quickly. What differences do I get? 6 minus 0 is 6. 6 minus 1 is 5. 4 minus 0 is 4. 4 minus 1 is 3. Now, how do I get the number 2? 6 minus 4 is 2. And the number 1 is 1 minus 0. And the number 0 is 0 minus 0. So the difference set is exactly set in x6 that has size 13. And again, that matches the expression if you plug in 4 into that formula. So that's a Coulomb ruler, really. And now you choose a Hermitian matrix with these eigenvalues, 0, 1, 4, and 6. You can choose a diagonal matrix or any other matrix with these eigenvalues. And then let's define a scaling factor that are all powers of 13. And then we set our subgenerators H1, H2, and H3 to be the scaling factor times this chosen Hermitian matrix. Then, okay, again, we plug everything into our formula for the frequency spectrum. We get set in x6 plus 13 times set in x6 plus 13 squared plus set in x6. Again, I claim this is a set index 1098. In this case, we don't get gaps, but if you increase the number k, you get gaps, as you can prove. And again, let's check it if our previous formula is correct for this example. So what is the size of this set? It's 2 times 1098 plus 1. That's exactly 2197. And that is exactly 13 cubed. And that matches this expression here. Yeah, 4 squared is 16, minus 2 squared is 12, plus 1 is 13, and 1 times 6 divided by 2 is 3. That's exactly 13 cubed. And you see, we get with a single layer model and 6 qubits, we get 1098 frequencies. Yeah, and compared to the case, if you choose constant subgenerators, two-dimensional subgenerators, you only get R times L. So in this case, 6 frequencies. So you see, okay, you can enlarge your frequency spectrum very much. Okay, for the end of my talk, let me give a summary and outlook. And I don't mean the Microsoft product. What we learned. First of all, we learned, okay, a quantum neural network can be represented by a finite Fourier series. And we have seen that the so-called frequency spectrum of a QNN relies only on the ansatz chosen, so on the generators, subgenerators chosen. Then we have seen 3 maximality results in the frequency spectrum, and we constructed concrete examples how to construct QNNs with maximal frequency spectrum. Now, I said it earlier, what now remains is, okay, we can maximize the frequency spectrum now. We know how large it could be maximally according to the maximality definitions. And the question is, what impact does it have on the approximation quality? So we already did some computations and simulations, but because the frequencies, more frequencies means less freedom in the Fourier coefficients, it could be that making the frequency spectrum large, that the approximation quality drops. And yeah, so this could be suboptimal. And so benchmarking different ansätze is the next task we want to do. Yeah, so now we want to go in practice and see, okay, what is the quality if you choose these types of ansätze? If you're now curious about these results, you can take a look at our paper. It's available on arXiv at the moment. Yeah, and now I want to say thank you for your attention. And I'm up to questions.
Wonderful. Thanks a lot, Patrick, for this wonderful talk. And I found it pretty interesting, specifically because you took a different narrative and talked about the mathematics behind all the QML algorithms you know of. So this was pretty interesting, and I assume the participants might also be motivated to look at all the QML algorithms they're working on, or probably they work on for the projects. From a mathematics standpoint of view, dive deep into the algorithms, try to do with the primitives and the functions, also the fundamentals, and try to optimize the algorithms themselves. So thanks a lot for the talk, Patrick.